Quarter past. Should we wait a little bit? Oh, yeah. Okay. Yeah. You can start.
All right. So it's my pleasure to welcome you to the master thesis defense of Giorgio Garetti, who has been with us for 1.5 years. Yeah, even more. Projects and lastly, master thesis this thing ended in a few days ago. Not too long
Yesterday.
But we've in fact been very fortunate that someone would offer to read it also. So, one important person besides Giorgio is external examiner Martin Medum Nielsen from Technical University. Somewhere out there, X-ray physics, scattering. And of course, Peter Koster has been the main supervisor and brain behind it. Who will now give a lecture of between say 30 and 45 minutes, depending on pace, so on. And then afterwards we'll have discussion. Meeting and maybe someone who wants to learn about what you do. And then the whole thing will end. We decide whether we pass or not. And that be great. But firstly, your lecture, please go ahead.
Okay, so a disclaimer first. I am recording and streaming the thing live. So if somebody wants to ask a question and is worried about privacy, just say that before asking the question and we'll stop recording. So just go ahead and trouble. So never know. So as you may have guessed from the title, today I'm gonna talk about indium arsenide nanowires, and in particular about substrate preparation and growth dynamics. But let me define the playground first. So what I've been doing during this project lies in the intersection of these, let's say, macro areas. And for instance, if you take nanofabrication and thermodynamics and kinetics, you end up having nanowire growth. Then if you take structural characterization, such as X-ray and electron microscopy, and you interweave it with thermodynamics and kinetics, then you get growth kinetics. And right inside, well, there is me, some coffee, and some other stuff, and my project. And in the intersection of all these things, a lot of interesting things can happen. But this also implies that during this talk, I will not be able to go in details in any of this, unfortunately. So the outline of my talk is as follows. First, I will introduce some of the basics that are required to understand what I'm talking about. Then I will present some of the results on the fabrication of substrate for nanowire growth. And then I will present some of the preliminary results on the growth dynamics. So it's time to dive in. Right, so let's start with nanowires. As you may have guessed, they are like the king of all my daily activities. But what are nanowires? So nanowires are freestanding crystals growing in well-defined direction with well-defined outer morphology known as faceting, and with a controllable crystal structure. Their dimension, as you can see in this scanning electron micrograph here, range from hundreds of nanometers in their width to up of tens of microns in their height. And these dimensions are particularly interesting because they make nanowires to be the perfect platform to perform a lot of fundamental studies in all these physical phenomena related to size effects, such as quantum transport, optical measurement, and you name it. So on the right side, you see a very toyish atomic model of what a nanowire looks like, where you can see what I said before, the faceting, In this case, these are well-defined crystal plane belonging to a specific family. And underneath that, you see the versite crystal structure that is creating this nanowire. Since I named the crystal structure, let's dive in on what actually are crystal structures possible for nanowires. There are mainly two big families, the zinc blende and the versite. And the big difference between these two is that the zinc blende is a cubic system, whereas the versite is an hexagonal system. Another big difference between these two families of crystal structure is that versite is only seen in nanowires, 3-5, well, not 3-5, 3 arsenide, whereas zinc blende is seen only on the bark. The big difference between this crystal structure is best seen if we look along the growth direction, which is this vector here, and we call the growth direction using Miller indices, either the 1, 1, 1, and with C, I mean that I'm using the coordinates from a cubic system, or the 0, 0, 1 if I use the hexagonal coordinate system. They are the same direction, it's just two different names. And again, it's this direction. And the big difference lies in the stacking of atomic planes in this direction. So for instance, for zinc blende, we have A, B, C stacking, meaning that the B plane do not sit on top of the A plane, and so do the C plane. Whereas in the versite, the stacking is AB, naming that B doesn't sit on top of A, but A sits again on top of the A before. Zinc blende can have a kind of a variation, especially we call it twin zinc blende, and it happens when we insert one single layer of versite in the stacking, and what the single layer does is rotates the whole structure by 60 degrees along this axis. And so this structure and this structure, although they are the same, they are actually not the same because the symmetry of the zinc blende around this axis is threefold symmetric. So a 60-degree rotation will not give the same structure again. And we call it twin because twinning is the phenomena where a part of crystal is rotated or it has a certain symmetry operation that relates it to another part of the crystal. And how do actually nanowire grow? I will try to present a very simplistic model, and the more sophisticated models are, you can read some on my thesis on literature. And the main mechanism that is behind nanowire growth is called the vapor-liquid-solid mechanism, VLS for short. And it starts with a substrate, and I will spend more words on what are these substrates later on. But basically, it's just a slab of a semiconductor with some kind of catalyst particle. In my project, it's only gold, but it can be something else, deposited on top. Then, as soon as we increase the temperature and we reach a growth temperature, keeping on arsenic back pressure to avoid ruining the substrate because arsenic is very volatile above 300 degrees. Then what happens is that the deposited gold particle will start to alloy with the substrate, forming this droplet of a liquid alloy. As soon as we open for another atomic flux, namely the indium flux, what will happen is that the gold particle will start to absorb, namely they will act as zinc, and they will absorb all the atomic species in the vapor into the liquid. And that is called supersaturation. And it will keep on supersaturating until it reaches a critical situation where it's favorable for the atoms in the liquid phase to actually precipitate, forming a crystal in a solid phase. In thermodynamic language, this mechanism is just a Gibbs free energy minimization process. And the key parameter to determine what happens is the chemical potential mu, defined, as you can see here, using this fundamental equilibrium thermodynamic equation. And so the criteria in thermodynamic language to have nanowire growth is that the chemical potential of the vapor must be greater than the chemical potential of the liquid, and in turn, they both must be greater than the chemical potential of the solid. And this means that an atom in the vapor phase will go in the liquid phase, and then we go in the solid phase. In this equation also lies a little secret. That means that we are actually very far away from equilibrium if this happens. And that means that actually we shouldn't use like the classical thermodynamics because they are valid at equilibrium or very close to equilibrium. But for now, just keep this mechanism in mind because it works as a very intuitive model to understand how nanowires work. But how do we actually grow them on a daily basis, so to speak? And we use a machine called molecular beam epitaxy, MB for short. And you can see our setup here at Niels Bohr Institute, and it's composed by some electronics, a lot of pumps, a vacuum chamber. Down here we have what we call the fusion cell, which is like the responsible for this atomic beam flux that I was talking before, and then some load lock to exchange the sample. The key points about the any molecular beam epitaxy system is that inside this crucible we have high purity materials, which give us higher purity beam fluxes. And moreover, since we are working with very high vacuum, our system has a base pressure around minus 11 torr. The whole system is virtually free of any external impurities. Lastly, we are able to control the basic growth parameters very easily because not only the beam fluxes can be controlled by tuning the temperature of the cell, but also, for instance, the temperature of the substrate can be controlled. So we now turn our attention on the substrate. And as I mentioned before, substrates are just the semiconductor slab with some catalyst particle deposit on top. So now I'm going to just give you a brief fabrication process overview. Then I will spend some more about the position and the size control of these catalyst particles, and then show some results of this fabrication for substrate for nanowire networks, and also spend some more on a novel family of substrates we developed, namely indium arsenide with a thin film of silicon dioxide. So how do we actually make this substrate? Well, we start with this famous now slab of semiconductor. Then we deposit a polymeric resist that is sensible to electron beam exposure. Then with an e-beam lithography system, we expose the desired features. And with some chemical development, we end up with a situation like this. Here you can see a side view and a top view. And mainly what we have done is we have created a mask on top of our semiconductor slab. We then use some chemical or physical cleaning processes to make sure that nothing except the semiconductor is left inside the hole. We then deposit with electron beam evaporation, gold inside the hole. And lastly, we lift off, meaning that we just get rid of all the unwanted polymeric resist and the unwanted thin film on top of the polymeric resist. So the end product is what you can see here, side view and top view, where we have the semiconductor slab with this well-defined golden droplet. A scanning electron micrograph of the substrate as made is shown here, where you can see, I guess, what is very hard to see here, namely that we have deposited these very nice cylindrical things. During the gold deposition, we can easily control the height of this droplet. Moreover, as you can see here, this is now a grown substrate, so these little things sticking out are actually nanowires. Should tell you that we are able to design pretty fancy arrangement of these gold particles. For instance, this thing here, it's an alignment mark, and it's just a cross. So the limit of the shape that you can draw just depends on your creativity. So I thought about size control. The first thing that we can actually tune, as I said, is the amount of gold we deposit inside the hole. But the second thing we can control is the width of the hole. And the way we do that is by tuning a very important parameter, the dose, which is the amount of electron per unit time that we deposit into the polymeric resist. Here I'm showing for two different acceleration voltages the radius as a function of this dose. And what you can see here is that we have a great tunability from 60 nanometer up to almost 200 nanometer. The error bar of this measurement are just the standard deviation of almost 1,000 radius measurement of the gold droplet. The take-home message from these two graphs is that, yes, we can tune the size from 60 to 200 nanometer, both using 30 kV and 100 kV, which is a high acceleration voltage, obviously. But the precision in this control is way higher if you use 100 kV, as I guess you cannot see because the error bar are super small, but they are somewhere here. Also, the low acceleration voltage has another problem, namely what is called the proximity effect, which is created by the backscattering of electrons during exposure. And what you can see is that for a given dose, the size of the exposed droplet depends on the density of the feature around that droplet. So if you have a high density, which is most a small pitch, meaning the two dots are very close together, then we will get a wider hole compared to if the array is very sparse. This thing doesn't happen at all if we use a high acceleration voltage. And that is pretty nice because that means that we can actually design whatever shape and whatever array we want, and we can always get the same width of the hole. I guess you may be wondering, why do we care actually about being able to control the position and the size of this catalyst droplet? The first thing is that the catalyst volume controls the nanowire diameter and the growth rate of the nanowire. In turn, the nanowire diameter can control some properties of the nanowire. So if you want to use nanowires to perform this aforementioned fundamental study, you want to have always the same width and always the same length. And for instance, it's also well known that the electromobility nanowires is dependent on the radius of the nanowire. So it's pretty important to be able to deliver nanowire with a controlled radius. Lastly, and this is kind of a spoiler alert, the catalyst position allows us to craft a substrate that allow to create nanowire networks. And that's what I'm going to talk about now. So what are nanowire networks? A nanowire network is a network of nanowire. And the way these kind of networks are created is by first growing a straight stem, then by tuning the growth condition in such a way that actually gives rise to this kinking event, we can make the nanowire stop growing axially, but actually growing outward from the facet. At some point, if we have created a substrate that is actually good enough, we will observe that the nanowire merge. And this is the first step to create a network. But I will not spend word on how we actually kink the nanowire, because that's not what I've been doing, but actually I will spend some word on how do we make sure that the kink nanowire will actually meet forming a network. And the way we do that is by designing a hexagonal array of dots, or droplets if you want, and we are then able to align this pattern with respect to some of the crystal direction of the substrate. We know that our nanowire have facet in these two families, either 112 using the cubic indices or 010 using the hexagonal indices. And as I said before, we also know that then the kinked wire will go outwards from the facet. So the cool thing that we can do with in beam lithography is that we can define this hexagonal and align this side of the hexagon with the 1 - 1 direction, so that we are sure that in the end, if the kinking event happens and the nanowire grows, they will eventually meet. This direction is chosen because it's actually what is called commercially the major flat, which is mostly the most probable cleavage plane. So that allows us to actually visually align our design with the substrate. So down here, you can actually see the same step I showed schematically above. And so here you see this droplet defined in a hexagonal pattern. Here you see the straight stem growth. And here you see that actually the kinking event happens and the nanowire do merge along the direction we want. And nanowire networks are pretty interesting because they will eventually be one of the base systems to perform, for instance, braiding of Majorana, or just to build the future transistor if we keep on downscaling our technology. So next up is another family of substrate. This is what I called before the silicon dioxide thin film substrate. And the fabrication process is exactly the same as before, but we have two new steps. The first one is that before depositing the polymeric resist, we actually deposit a thin film of silicon dioxide. And another step is before depositing the gold, we then use argon ion milling to make sure that we actually create holes in this thin film we deposited, and we calibrate the source so that we are sure that we are just touching the indium arsenide. So this will be silicon, then this will be indium arsenide, and this will be silicon again. So the end product of this process is shown here, where you can see this red thing here is the silicon dioxide thin film. This is the bite of the starting indium arsenide semiconductor, and this is the hole that we drilled, and this is the gold sitting inside this hole. This is a cross-sectional tilted image where I cleave the substrate right here. So what you are seeing is exactly how it looks from the side. What is so cool about the silicon dioxide substrate is that in the first place, nobody in the literature reported to be able to grow on this substrate. And that is because the dynamics of the growth change dramatically when you mask the substrate with some material that is, for instance, silicon dioxide. And also the extremely cool thing about this substrate is that they may allow to perform X-ray studies just getting signal from the nanowire, because the underlying substrate is altered in some way. And that brings us to the next big thing, I would say, and wouldn't it be cool actually to be able to see nanowire as they grow, to understand how they actually grow in details? And the answer is indeed yes, it would be immensely cool, but literature is kind of scarce. There exist, to my knowledge, just these three main papers. One is done in this group, and another one is done by Francis Ross's IBM, and the other one is done by Scott Now at Los Alamos National Laboratories. And the big difference between this paper and these other two papers is that in this case, X-ray has been employed, and in these other two cases, it's a transmission electron microscope. The big difference between these two techniques is that using X-ray diffraction, we actually get averaging for free. That means that we can look at a lot of nanowire at the same time. Also, we can use very realistic growth conditions, whereas in a TM, because of the requirement of ultra vacuum of the electron gun, the beam fluxes are usually extremely low compared to what we want to use to grow nanowires. Lastly, as I said before, here we get statistics for free, and using a TM, we are actually looking at just one nanowire at a time, which is not optimal. So to perform this in situ study, we flew to Japan at Spring 8 at beam line BLX11, well, BL11X2. And what is so special about this beamline is that they have this awesome setup you can see here, where you can see a surface diffractometer here and an MB attached to this surface diffractometer. And that allows us to grow, to shine X-ray, and to measure the scattering of X-ray as we grow. So the setup is pretty straightforward. This is, as I said, the surface diffractometer. This is the vacuum chamber. Somewhere here is the sample, the diffusion cell. The X-ray beam is coming from here, and the detector is hidden somewhere here. So let us remind for a second what is scattering from a crystal. We all know that if we consider an infinite in three-dimension crystal, what we get when we shine X-ray on a crystal is we get scattering from it. And the scatter amplitude will follow this simple equation where we have a structure factor that just determines the scattering from a single basis, in this case a unit cell, and a lattice sum, which just determines how the scattered waves from every single unit interfere between each other. And the result of the scatter amplitude is that we are able to measure an intensity that is very well defined and that follows like a delta function kind of shape. That means that we have a very high intensity at the breakpoint. But what happens if we now lose the constriction of having an infinitely big crystal? So what happens if we now start with our original, let's say, infinite in three-dimensional crystal, and we want to slice it somewhere to create a flat surface? And the procedure to do that is just taking a crystal and then some kind of shape function that we cut our crystal. In the end, we get a cut crystal, a truncated crystal. And this is this operation here. The scatter amplitude of such a truncated structure is found to be just proportional to the original scatter intensity from the crystal times a new factor. And this new factor is just diffuse intensity around the break peak in a direction that is normal to the surface that we created, and with an intensity that goes down if we go far away from the surface. In general, this shape function here depends on, of course, on the shape of the truncation. This 1/k thing happens only when we consider a flat surface like this, but we can say that in general, whenever we create such a truncated structure, we observe that the scattering is no longer localized in these break peaks, as I said before, but around the break peaks. And the volume reciprocal space that is that we observe is inversely proportional to the size of this truncated structure we create. So you may be wondering, but yes, this is all cool, but what did you actually measure when you were down there? And I will show you now. If it works, well, it's not. Yes. So what you're seeing now is what we were seeing when we were back there. So this is a program I developed to be able to actually understand the measurement that we were doing. What you see here is an image of the detector, and this is reciprocal space. What you can see here is that at the beginning, before starting the growth, we only see something here, and this is the break peak coming from our substrate. Then we start the experiment, namely we start to grow. And what happens is that if I now slide this thing here, I'm sliding time. So I'm going forward in time, and we are starting the growth. And you will see that slowly, something starts to happen, exactly at this point. And now we have two new peaks. This is now the twin zinc blend that is growing, and this is the versite. So these are the signal from our nanowires. And you can actually move around a region of interest to see exactly how things looks, and so on. And this is pretty cool because this actually tells us that we can see in real time what happens when we grow or we change something during the growth. Slides. So now I'm showing you an overview of such a measurement. For instance, here you can see a characteristic detector image taken at some time during growth, highlighting the region of interest that we want to monitor. So we have a region of interest around the twin peak, which is twin zinc blend, a region of interest around the versite, and then another black region of interest around the CTR rod. And you can see the intensity evolution as a function of time right here. What we have done during this experiment is called the growth interruption. That means that we start growing, then we stop, then we start, then we stop. And it's known that doing this will actually alter the crystal structure of our resulting nanowires. Unfortunately, there was kind of a problem during this measurement, so we should divide the growth experiment into two parts, and we call this one before 1,500 seconds the beginning of the growth. And you can see that some strange thing happens, namely the nanowire seems to grow, then suddenly stop, and then do some other stuff. And we assume that this is actually not a physical effect, but rather a problem of our measurement in the sense that it depends on the position of the detector in real space and the way it slices the peak. But the interesting science happens here. At a certain stage of the growth, you can see that this crystal truncation rod seems to wiggle about. And the intensity from the versite and the twin doesn't seem to change much during this growth interruption. So let me go back to the crystal truncation rod. As I said before, as soon as we truncate a crystal structure, we observe these rods of scattering in reciprocal space. So up here you see the real space picture of our nanowire, and down here you can see the reciprocal picture of this nanowire. So we see now this is the position where we expect the versite peak to appear, and indeed it's here. But we also see rods of scattering expanding in this direction. And we know that this direction is actually comparable to the real space direction of the width of the nanowire, whereas this L direction is the growth direction in real space. And then we see that these two rods are actually created by the fact that the nanowire has this well-defined facet in the side. And we also see that we have a truncation here and a truncation here, and they are created respectively by the fact that the surface of the substrate is indeed a surface, is not infinite, and also that we have another interface here that is truncated. If we now switch and look from the top view, and this is our reciprocal space map done by Thomas, we can see how a nanowire looks in reciprocal space if we look through the growth direction. And here schematically it shows the facet of the nanowire, and here you can see again that there is one truncation rod per facet. And why do we care about all of this? This is because, let's say, the main break peak is not really sensible to whatever happens here. And we are really interested to see what happens here when we change the growth condition. Namely, what crystal structure do we get if the growth, the condition of the growth front changes? And to do that, we go back to our detector image as before, and now we select should I say, smartly, some region of interest that actually are monitoring just the dynamics of the truncation route around the versite peak and around the twin peak here. You may ask immediately, why do you think that monitoring this region of the twin is something smart that you want to do? And that is because we assume that because of this anti-correlation within the signal, this signal is indeed coming from the nanowire. It would be kind of strange to think that the substrate reacts in this way. So we form versite, and at the same time, the twin is disappearing. And that cannot happen on the substrate because the versite cannot be created on the substrate. And what we see here is that we turn in the indium on, and as soon as we do that, the versite intensity starts increasing. And that means that we are creating layers of versite at the growth interface. Then when we close for it, the versite goes down, and we assume that what's going on is that the versite is reconstructing into a zinc blende. And then if we do that again, the same happens. And it happens again, and it happens again, and it happens again. And this is pretty interesting because it means that by tuning the growth condition, we can control which kind of crystal structure is created at growth point. And this alone would not be approved, but we then performed some ex situ high resolution transmission electron measurement done by CRAM at Max Planck Institute in Düsseldorf. And what we can see is that we can actually correlate these aforementioned changes in truncation rod to actual changes in the crystal structure. And we see that here we start with a versite, here then we have a slab of twin, then we go back to versite, then we have another slab of twin, another slab of twin, and again. And this is pretty interesting because that means that we can not only control them, but we can actually see the change in crystal structure in real time. In this slide, I'm just showing you a representative scanning electron micrograph of how this nanowire look after the growth. And here is just a zoom of one single nanowire showing the nice faceting that we expect from a mostly versite nanowire. Lastly, as I mentioned before, we created this silicon dioxide substrate, and we actually used them during this experiment. And what this substrate allows us to do is to change the growth condition of this parasitic growth, as we call it, which is the growth that happens in between nanowires. And if this substrate was not covered with a silicon dioxide thin film, we would not have observed this kind of growth, which, as you can see, only happens around the root of the nanowire. In between, where there are no nanowires, we can almost see no growth. Not only that, we can only characterize this parasitic growth using Lauer fringes oscillation. So we just take slice along the L, which is our growth direction, and we take the derivative of it, and then we observe that as a function of time, the oscillation of the Lauer fringes gets bigger. That means that we are actually growing some kind of layered structure with the height of this layer that is getting smaller and smaller as we grow. And this was never observed or measured before. So this actually brings me to the conclusion and the acknowledgement. So during my project, I was able to fabricate some subjects that gives us a very high control over the size and the position of our catalyst, and I explained why this is important. Also, we got the first, and I would say, promising result in the creation of nanowire networks. And lastly, we have seen how in situ X-ray scattering can give us a lot of insight on the dynamics of growth. Obviously, acknowledgement. Jesper and Peter, thank you for having been my supervisor. Everybody in QDev, especially Torvald and Harry and Martin, for helping me yesterday to react the slides. And well, funding, Danska, thank you for paying the trip to Japan, and also the Danish National Research Foundation and Station 2 for funding most of the lab business and most of all non-profit.
So, any questions? Those will be posted, I think, by us mainly. But if anybody has to leave before this event, then I have to do before.
No, you can't.
But feel free to stay and Team making the slides.
Hmm?
You had a team preparing the slides?
Yeah, exactly.
That's fine.
Damn! Should have said that. Let's say that I originally miscalculated by a factor 1 hour how long my task would have been. And then we like prepared, like I showed the task to them and said, we should maybe have some time. And then required kind of a lot of work. That's
So it's good.
yeah. Yeah, actually, also thank you for like not having needing as amount of time.
So you're ready. Actually, firstly, I have a simple question. As I mentioned, you were doing a project before.
Yeah.
Maybe it's good to clarify. So what was the project and when did the
Actually, I think
thesis
none.
start?
Yeah, none of the results I showed were part of the project because when I started the project, one machine was working and the other one was not working, and the machine that was working got completely abrogated when I started the thesis. So all the work I done before could not be reused. So
What you've shown there is really your thesis for you.
yeah,
And there's some data in your
yeah,
thesis.
some of the appendices of the thesis were like brutally adapted from the project, but I think I. Yeah, I think it was not like a big bolt, kind of like this Italian turning.
Yeah. So, do you want to?
I can start, certainly. First of all, I would say that it was a pleasure. That it's nice to see little footnotes in between. I like the. I mean, obviously, you get the impression that this is your own style of writing. It's it's a refreshing change from the more dry way you write papers. I actually enjoy it. And I like the little footnotes, and maybe I should just start with one of them because you want picture 11. From a footnote that says footnote 4, it's subtly assumed that the scattering is perfect. And the scattered photon does not lose any energy in the scattering. This is not true for This is largely true for all elements in this thesis, but it must be noted that inelastic scattering can happen, especially near the absorption edges of the material. I like this. So I should say, so I just have to ask. Sure. Since you put this, and you sort of invite these questions, and I like the opportunity, because you say this is largely true for all the experiments in this thesis, i.e., that they are inelastic. So why largely? Are they not inelastic?
Oh, it's largely because if any non-elastic scattering event would happen, we would not notice that. Because the analysis we're doing is just considers that all the, let's say, k prime and k, which is scattering vector, scattered vector, we just consider them to be the same for like all dynamics that we want to explain.
So what would be largely?
For instance, it's just that inelastic scattering would happen if we have multiple scattering events, for instance, or if something gets absorbed in the material, that would just give a different scattered k prime wave.
Multiple scattering events.
Yes. For instance, in a crystal, if Well, that's a good question. So multiple scattering events is that, so we assume that as soon as the wave is scattered from our material, it goes out. But then it could also happen. Yeah, it's called the kinematical scattering. But it could also happen that it just goes back again, and after multiple collision, then the energy loss can be definitely significant.
Where could you have multiple?
I think, for instance, in a layered material on, well, in an X-ray mirror, for instance, you definitely have we're close to the absorption edge for, and if I think also if you're very close to the glancing angle, then you are definitely close to get a lot of absorption. But then it will actually just propagate through and then get emitted again. So no.
Multiple scattering.
Yeah, absorption edge. Yeah. Yeah, true.
Okay, but before leaving this, when you say inelastic scattering, can you give valuable information?
For instance, I guess as soon as, for instance, the X-ray wave gets absorbed, then you can actually understand how much energy was lost, so how much energy was absorbed, and that in turn can, for instance, help you to understand like the electronic properties of the absorbed material. I think, for instance, SANES and like near edge absorption X-ray spectroscopy usually employed to this thing to get information on the.
But that's not really inelastic scattering.
No, it's not. Yeah, that's true. Okay. Yeah. 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 Then any X-ray absorption measurement will just give you valuable information by measuring the energy loss.
Right. Okay. But as you probably, as Jesper already said, so I would probably focus a little bit on the experiment that the questions for the same supervisors. So, but I would like to jump right to it and ask you a little bit about the figures that you have. This is figure 3A. Those who showed it during the presentation. Come on page 37. This one. That's one. All right. Actually, the other one.
Okay, like so.
Yeah, maybe. Yes. Okay. During the presentation,
yeah,
you said something about. Obviously, when I see these kind of things, it's all well and good that you say something about the late time.
Yeah.
But I would say, well, what's going on in the early time?
Yeah.
Is there anything? Can you understand what's going on there?
Let's say yes and no, and I will try the best to explain what I understand about what's going on at the beginning. And so the point is that scattering actually happens in a volume reciprocal space, right? So if we consider, for instance, this is our K, this is our K prime, and this is our scattering vector, right? And this expands in 3 dimensions. So for instance, a Bragg peak, because of the finite shape of our crystal, is actually not just a single delta function in reciprocal space. It's more like a volume. So, and the shape of this volume depends on the shape of our crystal.
So how?
Well, I assume that it gets bigger as is if the crystal is smaller. But that also depends on the dimension. For instance, a very thin but long thing in real space will be then thin and long, but shifted by 90 degrees, for instance. So what has happened that, for instance, here at the very beginning, this sudden jump is not that the nanowire are just like on steroids and they just grow, but it's just that the Bragg peak is actually, as soon as the nanowire looks like something like this, it will just, for instance, have more a shape like this, right? And then if it gets like more and more, where like let's say B and H are very close together, then the shape of this thing will be more like this. And that actually will give rise, if this is our detector, for instance, that will give rise of a different record intensity, which may actually be lower, not because we have less nanowire, but just because the shape of the peak is different. That's how I explain it.
So the shape of the peak is different. How will that be?
I think because the way our detector is placed in reciprocal space determines the intensity. So it's the intersection between like our Bragg peak in reciprocal space and our detector that gives us our intensity, the intensity we measure.
Okay, that we need to discuss.
Okay.
So what do you mean when you say intersection between Bragg peak?
Okay, I mean that. So. So we have a scattering event, right, when our reciprocal space vector intersects the lowest field, right? And the way this intersection happens depends on like the shape of the function that is giving the peaks, right? So what I mean by intersection between the detector and our reciprocal volume thing is that the way the scattering, the rods look in reciprocal space changes the amount of, like how much do they actually cross our Ewald field. And that is actually the intersection that we measure.
Okay, yes.
That's
very good. Right.
That also means, for instance, if I may say that if we could place the detector very precisely, for instance, in the very center of the Versailles, and that is not so easy for the reason that the Versailles is not there before starting to measure, and also because the exact position changes as a function of temperature. So at raw temperature, the lattice constant of the Versailles is kind of bigger than the one we can measure at raw temperature because of the oscillation of our atom. So it's hard to do that. Also, I guess having a higher energy X-ray beam would help us making the Ewald sphere like more flat, and so it could be easier to actually make sure that the intersection is not sensible to the shape of the peak.
Can I just add a question, please?
Yeah.
So when you have a very tiny crystal,
Yes.
and it involves in the volume of the very small nanocrystal,
Yeah.
would the center of the Versailles maybe change its position?
No, I don't think so.
You maybe imagine that you have some strain if you have a very small flat.
Oh yeah, so I assume that, so if the lattice constant of our super small crystal is the same during this time, then the Bragg position, the peak of the center of the Bragg position will not change. But yes, if it's very small, then we may have more strain. That means that the lattice constant may change a little bit. In that case, yes, it will definitely move as we go.
So if we now continue down figure 38, so that was so you had an explanation for why it's as sharp lines.
Yeah.
So this is because we get more of the volume in diffraction.
Yes.
So what happens then? Then it slows down. If you look at the green.
Right here.
Yes.
Yeah, so that's what I was trying to say. To think that at some point the shape of the thing that is in the scattering condition may actually give rise to a decrease of the intensity because it gets like from this situation where it's like going exactly to the Ewald sphere, it will just get flatter and flatter, and at some point it will actually give like a smaller area, which gives rise to smaller intensity.
For these shape changes, how would you see those? Would you see those shape changes?
But not just by doing this experiment, I guess, but because right now when we are doing this, the detector is steady because we cannot move it while we are going because then we would not understand anything at all. But for instance, if we stop the growth, then what we can do is just what I called before the reciprocal space map that was done by my fellow Thomas at the X-ray group. What you can do is just to stop the experiment so your nanowire is frozen, and then you move the detector around the reciprocal space like this. And then you collect a set of images, and then you can actually go back and reconstruct the shape of your brag in the supercomputer.
So now you say you move the detector around.
Yes.
So if I understand correctly, then the image of 3.7 is actually in a what you get on the detector.
Yes.
So so there you have, for example, the side.
Yeah. Yeah.
So what would happen if you move the detector? See something?
Yes, definitely.
So if you move it by, say, a quarter of the distance in the vertical direction, what would be that?
Actually, so in this case, you have to move it to get something different. I would say that you have to move it in like this. So let me clarify. So in this axis, we have L, which is our growth direction. And in this axis, we have actually a combination of H and K, which is like our in-plane scattering vector. So depending on how you move like out of this plane, then you will actually intersect the Bragg volume in a different way, and this will give rise to a different shape.
So what happens when you move the detector?
Well, I guess you are just measuring in a different position in reciprocal space. So,
But, I mean, if I only move the detector, say, a quarter of the distance, quarter of the height.
oh no, then it would be the same if you just. So, yeah, okay, I see what you mean. So when I say move, you are actually to move the detector and get into, let's say, different scattering condition for like all the possible position in the reciprocal space. In that case, you actually map all the.
So my question is, by moving the detector, can you then change the diffraction?
No. Absolutely not.
Absolutely. Okay. So how would you then change the? How would you then, if you're not completely in scattering condition for the inside, how would you then, if you had all the time in the world, stop the growth condition, what would you optimize? You find it. I mean, if you're, let's assume that this is the image you have, and you say, could this be better? How would you then go about finding the inside?
I guess I've never done it, but what I would do is just to like move my detector around until I reach the maximum intensity of my Versal. And that's
if this is the situation,
okay.
Moving the detector change the intensity in the detector.
I think so. Damn. Okay.
What is the detector doing?
I guess it's just like the detector is.
You have already said the right things about it. I mean, what determines whether you get an infection?
Well, if the like our
you already said.
Yeah, our let's say our fraction broad intercept the evil sphere.
Yes. Yes. Yeah. That is. We hang on to this one.
Yeah.
So, will moving the detector change where the diffraction rod intersects the evil sphere?
No.
No. No.
Yeah.
So what are you really doing with the detector?
So I guess with the detector, I'm just like mapping the scattering intensity as a function of a position in the reciprocal space.
Yes. Oh, yes. So where you put the detector just determines which region of the reciprocal space is.
Yes.
Given the detector.
Yes.
So going back into if this was the situation, how would you optimize the? How would you find the optimum for the detector? What would you change if you were unsatisfied with the way the design was before?
Well, there's I think still two reasons why I would be unsatisfied. The first is that I'm not really in the Bragg condition for that first epi. Yeah. And then I will just change the angle of my sample with respect to the beam For instance, until I get,
Which
well, it depends on the setup, I guess, but in general, so if we assume that this is my nano I sticking out, the first thing I would assume is to change this angle.
so the grazing incidence. I mean, you didn't say this explicitly, but
Yeah.
but
We were close to that, yeah.
Geometry,
Yeah.
close to grazing incidence. So what? Okay, so what would happen if you change the grazing incidence? Can you imagine? Sort of, if this is the image you have on your detector, can you sort of imagine which way it would be? What would happen? Maybe if you draw the geometry, if you just draw the sample horizontal, then you have a glance and incidence angle, then you have a takeoff angle, and just seen from the side. Right? So you're scattering downwards, yes?
Yeah, well,
So,
yeah.
so yeah, that's okay. So where's the detector?
So the detector is somewhere here, for instance. Right.
Yes. So if you are in a scattering condition, then here you have a scattering vector that fulfills, that actually intersects this sphere.
Yes.
So how would this look?
Oh, I guess something like this would be my scattering vector.
I mean, the scattering vector, I mean, if you have it's a difference in momentum.
Yeah, it's a k prime, which is the momentum of the outcoming wave minus k. Yeah.
So if you just draw the normal scattering.
Okay.
Maybe it's easier.
How we don't I have better drawing?
So if you have this one, what would the scattering be?
Actually, it would be, I guess, this one, if we are.
Yeah, I mean it's a difference between the k vectors. So
yeah.
So how would it be on this drawing?
Oh, yeah, actually.
Okay, I mean it's getting a little bit on the.
I think it's
maybe going a little bit
something like this, I guess.
But yes, very good. Yeah. Okay. Okay, but really the underlying question here is really how would you change, how would you optimize the position of the pixel? Right? So now we are trying to we have discussed how would what happens if you move the detector. Well, we have established that it will not change the Bragg condition, it will just change the region of pressure focus phase of the detector. So the next question is then, would you produce a Bragg condition or a better Bragg condition by varying incidence?
I assume so. So let's imagine that, for instance, these two planes are the family, two planes of the family we want to measure scattering from. And then we will get, so we can imagine that we move this around, like say up or down, and then what we will get is that our scattering vector will just change. Yes. And as soon as we actually hit the exact, let's say, distance in reciprocal space, when our scattering vector is exactly the distance we want between this 1, 1, 1 or wherever place, then we will actually.
There is exactly one rod where this is the case. Do you know which one?
One rod?
One direction in reciprocal space where this is the case. If you measure truncation rods.
Yeah.
Yes, there's one truncation rod. One particular truncation rod for this is.
But doesn't it depend on which plane you observe scattering from?
There's one where it really matters what you.
I assume the normal to the plane would be the most sensitive.
So there's one. That works. The specular.
Okay.
One to measure the specular direction.
Yeah.
All the other rods, and I think including the one, do they contain an interface? they speculate?
I think they're always right.
They're all speculate.
Yeah.
Okay. In the dynamics. In that case, you're. Okay. I must admit, I had assumed that you were not sure non-speculative ones.
No, we are in
To
this
get lower
right.
background.
Yeah, no.
So you are. Okay. But then you're absolutely right. That's exactly what you need to do. Okay. Right. Okay. So maybe a little bit on the. So you're right that that you change the lattice constant and thus moving further away from the practice. And now I understand why. Because otherwise, if you measure non-speculative loss or non-sensitivity,
Yeah.
means to be exact. Right. So maybe going to figure 3.4, 3.5. Are they 3.5? Is the Laue oscillations?
It's
Did you measure those on the condition?
I think there. Wait, so I guess you are talking about.
Yes, this one.
So the way we measure this is we start from say our usual detector image like this, and then what we do is we just take a big region of interest around here, and then we just sum the intensity along this direction, and then we derive as a function of time what we get. And that gives us back this, what we call the fountain plot, which is the pinky plot, this one, where we actually see in the x-axis the time, and in this axis I call it QZ, but it's just because we know how to convert from like L to QZ. So this is just the direction of reciprocal space, that is the direction of the growth. And then we also observe the oscillation as a function of time on the derivative of the intensity. Actually, that's absolutely fair.
The derivative of the intensity.
Yes.
So the right with respect to time.
Yes.
So it's basically the changes in the intensity as function of time. Or,
Yes.
so
But the fringing is not in time. It's in reciprocal, in L direction. So
yes. So these are the changes in. So these are the changes in. You define some time.
Oh,
Some time, early time, which you said as this is the.
So our time zero is when we start growing. Actually, when we start recording some frame from that derivative.
Then you subtract that from.
Okay,
How
no.
do you get
Okay,
this
to generate the derivative, we just take a frame of what we do, and then take the next frame and just which is the next frame in time, and take the derivative, numerical derivative.
So it's the changes from time to time.
Yeah.
Not the changes with respect to something.
No. Yeah.
And this is then measured under which conditions? What are you doing while you're measuring? It's not a continuous approach.
Yes. So during this time, the X-ray beam is on, and for this particular experiment, we open the indium shutter here, so we started growing here, and then we just let it go for 12.
And so, why does this work?
What do you mean?
So what can you learn?
Oh, so what you can learn from these Laue fringes is, I guess, some information about how the nanowire is growing. In particular, you can assume, so if at this time in time, if all the nanowires were growing with a completely random growth rate and they at completely random height, then we would not see any oscillation here. There would just be uh, uh, they would just be averaging out each other. Whereas we assume that this time what we have is actually that the nanowire are really almost at the same height, give or take maybe 1 unit cell, and that they are actually growing, which is what we see with the derivative with the same growth rate. So in, let's say, half millisecond, they actually grow 1 unit cell.
So what does these oscillations reflect?
Oh, so that's I would say kind of hard to answer because they are directly not related to like anything that is easily to grasp, I guess. So the way we can understand this is by actually like modeling the distribution of our growth, of our length and our growth rate, and then calculate the scattering from such a distribution of objects. And then we see that this kind of oscillation happens exactly when at some specific length. But so this distance is not correlated to the actual non-wire length, but more to some to how fast they are growing. I think so.
So you're plotting the derivative of the intensity.
Yes.
Here in the now.
Yeah.
You see now the equation now oscillations into a derivative. So it's something new at every time step.
Yeah.
What's new at every time step?
It's the amount of material that is grown per unit time that is giving rise to the oscillation. Right?
Yeah. But what is the oscillation? So the period of the oscillation, what can you track out of the period?
Out of the period of the oscillation, we grab like the height of the new layer that is being formed.
Yes, in the derivative.
Yes.
So we get so it's what's new every time. So we get the maximum length.
Yeah.
It's a measure of the maximum length of the new.
Yeah, at a given time.
Which haven't been there before.
So if you go to you say at some point that that you like at some point after 50 minutes or so that it stops increasing and indicating that the growth conditions have changed. And you say that it's reasonable to think that the height of the combined with the height of the area, and thus so on. And then you say we also know that the cool down after 2 hours, the temperature increase significantly. We tend to rule out desorption since the cool down drops and thus the structure is stabilized. Another explanation is instead that the lattice crystal structure is changing. The temperature was moving both peaks out of the chosen ROI.
Yeah.
Okay. And the ROIs, I assume, are the little boxes.
Yeah, exactly. Yeah.
So my question is, could you check this?
Oh yes, and that's one reason, and the other reason is also that we are like also going farther away in the compressed condition for this structure. So as we cool them down, they are not where we expect them to be. That's so if we move the ROI, indeed we gain some intensity back. But for instance, for the reverse side, it's now far from, well, not far, not as close as it was before to the back condition. So that also gives rise to less intensity.
So if you wanted to be less sensitive to the back,
The sensitivity in terms of when you change the temperature.
well, they're sensitive to the exact. I mean, you change the what would happen to the diffraction field when you change the lattice space? basically coming back to the one that I was talking about earlier, that if you didn't measure perspective,
Yeah.
this would move the crank peak on the detector, and then it would be captured by measuring that. So you would be less sensitive to greater movement of the crank peak, but you will still have the data on the detector. Yeah, that's right. That's okay. But with less strictly, less this is endless. Okay.
1 hour already.
It's good.
Maybe I
That's all. Maybe we continue a little bit on this because this is the results. So, can you say something about the shape of this function? So you have the blue function, which is the intensity of the real side.
Yeah.
And then you can see there are some small bumps in the real side. And so what's that? It's because the nanowire is growing some weird way.
No, for instance, what happens here, if that's what you are referring to.
Also in the beginning, you can see it rises
Here?
quickly. And then
Yeah. So that is because during the measurement, to avoid the saturation of the detector, we had to plug in attenuation, and that actually changes a little bit our intensity. So at this point, it was just growing. Then to avoid saturation, we turned on attenuation, and then the shape here changed a little bit. And the same thing happens here, and then here, and then here.
So we should have changed the attenuation before.
No, because then the signal of nanowire would have been probably way too weak to be actually detectable with a decent signal to noise ratio. If we had a higher intensity, higher attenuation to begin with.
We should stay in the line of machine if we want to compare intensity.
Yes, so actually the problem of this attenuation is that although naively one could think that we can use the intensity evolution as a function of time, for instance, to calculate the growth rate by taking the derivative, then we must be sure that we are actually not changing the intensity with something else like the attenuation. Because at this point, we cannot find a way to directly calculate the growth rate from this data. We need to use the fringing and then model the system.
if you know the attenuation,
Yeah.
you're assuming that the intensity is proportional.
Yes.
With that.
Yes,
Make
but
it
for
possible.
instance, no, but with our problem is that, for instance, here, we were super close to being saturating a detector. So as soon as we realized that we like that attenuation, so it may also be that the intensity was just going like this, but what we measured was a slight derivation. And then when we plug attenuation, the only thing we can do is to like take this point and match it with the second data set that we get. So we may introduce some unwanted change in the intensity that would actually fade our measurement of the growth rate.
Maybe to detect the errors. How do you change it?
Okay, that's an interesting question. So we took different background correction into account, and I can actually show you. Maybe. No. You know how to move the bar of endure away?
That way. You make the window smaller. That bar is, I think, always there.
Must be away. Well,
And there's the X on the left that you might just go to.
yeah, I can just close it. So here we start. So okay, I can only show you the second step of the background correction, unfortunately. So the first thing we do is to measure flat field. So we have the MTMB at go temperature, and we measure a lot of frame that will take in account all the, let's say, spurious scattering from the edges of the beryllium, from the sample holder, whatever. And this is the first data that we take out of our measurement. Then what we do, so we had two different beam times. And in the first beam time, we were actually able to put what is called a small monitor detector ahead of our MBE. So we were able to measure let's say, the incoming intensity of the signal. And that is important because the way that beamline works is that the monochromatomes are included with nitrogen. So sometimes they actually wiggle a little bit. And that gives rise to noise. And in this beam time, what we do is actually we select some region where we can actually see the wiggling, and then we just perform a background correction with this data. And you can see what I mean by this wiggling. If I move our region of interest where we shouldn't have anything, and I guess, and this is what I mean by this is actually our signal that we corrected for, and the beamline staff and Thomas also agreed that this is a characteristic shape apparently that I don't have enough experience of the temperature changes on non-kinetic. So that's how we take that.
One more that to measure the intensity in the condition.
Yeah. I think we did not count for them.
I think we took the overall thing. You have before you have any depression into your CCD.
Yeah.
You have the Boolean window.
Yeah, that's the first thing that we take out is what you call the flat field. Okay.
But also when you are growing things, you will have small domains.
Yeah.
So yourself.
And
you have disorder.
Yeah.
What would disorder?
Just create some like diffuse scattering. And no, we didn't take it out. We just let it be.
Just off the beat that in the way where you sort of estimate the diffuse
scattering. Well, if I knew what was giving rise to the diffuse scattering, then maybe I could model just a complete disordered polycrystalline system that gives rise to some kind of circular feature.
Intensity means that's not so intensity that is not in the exact condition.
Yeah, that's actually diffuse. Yeah, but then I may also like change the intensity of my truncation rods, which I don't want to change because I'm feeling how actually the intensity of this rod is changing.
Yeah, but if you have diffuse scattering, that what would happen if you have scattering from small disordered domains and your truncation? What would the net result be?
Just, I guess, background shift, align subtraction.
So it would give you a background to the intensity, and that would contribute to if you just integrate whatever you have on your peak, it will also contain.
That's right. Yeah.
The background you could estimate.
Yeah. Okay. Yeah. We will try that.
So that's just a window.
Yeah, where we are sure there is nothing.
Next to the, sometimes you also do a frame.
Yeah, but actually we can. Now that I think about it, now that you mentioned, that's what I cannot show you, the step that I cannot click. So, which is the result of this thing. So this is so to normalize, but for the incoming beam and diffuse scattering, we select in this for this particular one. This is just the first thing, and this red area is what we use to take out all the diffuse scattering and the shape of our incoming beam. Yeah.
Excellent.
Then you get it.
Yeah, in Mongo.
Can you go back to
sorry for not getting
No. Yes.
So we can see that if we are saturating the sector, then it starts to decrease, and you see this nanowire growth seems to be quite minor in the beginning.
Yeah.
That was what we assume at least. We have a liner machine. But we see at the end the rear side peaks start to decrease in intensity. Yeah. It seems like twin is just keep on rising.
Yeah.
Can you comment on what you think is going on?
I assume that that is because of the dynamics of the diffusion. So it's reasonable to think that at this, well, somewhere here, our nanowire are long enough that the diffusion length of like dead atoms is actually shorter than the length of the nanowire. So they will not have time to arrive to the growth front and thus contribute to axial growth. Or it could also be that the nanowire is so tall that they're actually, so if we have a forest of nanowire like this, they could also be doing what is called the shadowing effect, namely that the collection areas of an atom in the side facet is now smaller than if they were small, like, not so, definitely. If they were shorter, then the collection area on the side wall may be bigger, because they have less shadow. One is shadowing less than the next neighborhood. Okay.
Imagine that you have the real side structure in basic nanowires, and the material hits the side facet. Let's say it does not be incorporated at the growth interface. Actually, goes regular. What kind of structure would you have? If you have a real side structure, then you go regularly.
Perfect.
Yeah.
You just like
you
change the radius.
You will not change the crystal structure.
Yeah.
Correct.
Yeah.
But we see that kind of decreasing growth rate. So I think the first explanation is more recent.
Yeah, I think so.
Like it moves around and then you find steps
at the substrate where to actually be incorporated.
You show in the figure just below there. We can use the law of the oscillations in our bridges to say give an exact, very close to the exact length of the maximum height of the but we can also see that the oscillations become smaller and smaller as the nanowire grows longer. Then you cannot really resolve these situations. But how far can we go? Because when we look at this on the right, we can see it's like the oscillations is more prominent at the maximum time. Right?
No. The oscillation gets, so as the time goes on, the oscillation gets, the period of the oscillation gets smaller and smaller.
Yeah.
So
if we look at the oscillations in the graph here, can you point at an oscillation?
For instance, you can see, let's start, for instance, time 100, which is the red line, doesn't have any oscillation. It's just this red line. Right? Then we have time 200, which doesn't have any oscillation as well. Then we go to...
Yeah, but that's where we should see an oscillation.
Nope. Here we shouldn't see anything. We didn't. So we open the shader right about here, and then nothing happens until here. And then it's just at time 220, whatever, which is the purple line here that we see the first oscillation. And then the second oscillation is just smaller, and then it's smaller again. And then we arrive to the very last oscillation where we are close to having 1 pixel wide oscillation.
But it seems like they are very clear, these oscillations at 250. Could you go further and get more oscillations?
No, we couldn't. Actually, I think...
So there's a really sharp edge where it just disappears.
Yeah, so after, I think, 350 or 400, I think if we had like an immensely expensive detector with 1 million of peaks, actually no. If we could create a detector with small pixels, then we could be able to resolve this better. But at this time, our oscillation is maybe less than 1 pixel wide. So we cannot possibly like either detect it or be sure that there's an oscillation because a fluctuation on the
so we can only determine the growth rate of the between.
Yes.
We can't sometimes do something else when we go for a longer time, and we use this information to say something about the growth rates longer times.
Yeah, what we can do is to actually model this oscillation, and we actually, I think we are working in progress on doing the fitting right now with Thomas, and we can actually then extrapolate the growth rate And what we have seen is that using just, let's say, a Gaussian distribution of length and growth rate, we can actually match the XC2 length of the nanowire to a precision of about some nanometer.
But you have an intensity, and you can use this intensity where you have certain length of length.
Yeah.
This is
yes.
This was maybe you have to.
I have a long list of questions, but I think I will most of them for a more technical review. We all know that you probably put a mania into working into at night. Okay, development and optimization and needed for the experiment, but maybe there's not so much science to discuss. But we are certainly aware of it. Maybe you would just describe, say, your dreams of it as it looks now and these networks are being developed. And maybe what are the key features for making complex networks? Parameters, size, position, categories, and all these things.
Yeah, so I think that the key parameter is being able to control the size of each individual droplet. So we can design a substrate where we can actually make sure that, for instance, one droplet is small and the next 5 are big. That would give us immense freedom of creating different kinky structures. And also, we also need to find, let's say, a better way, which right now I don't know what could be, but we are aligning all our design with a cleavage plane of the substrate. And that is precise enough because the precision is less than 1 degree. So, I mean, unless the nanowire is 10 meters long, that little offset in the angular direction doesn't really matter. But that is actually, we are never 100% sure that our dots sit exactly in the, let's say, one direction of the crystal where we want them to sit. So, and that could be improved somehow, but I don't know yet how. And then there's the speed, which would be awesome to have a very fast way. For instance, instead of using imprint lithography, one could think about using nano imprint lithography, where you create a mask that is static, and then you use and very quickly punch through the substrate, and there you have probably 15 meters. That
was our next question.
Yeah.
Yeah. That has been shown to work. Fine.
It has been shown to work, I guess, on indium phosphide, if I remember that nanowise. But I think the biggest disadvantage is that the flexibility of the technique is less than in majority, because once you have made one of these stamp, then you cannot change. So if you, for instance, now want to make longer L-shaped nanowire, you have to make mask. That actually making the mask requires time and actually a considerable. But it would be nice for, let's say, the general substrate mass production.
Another thing where so you have hands-on experience with the EMV system at the synchrotron?
Yes.
Pro-wise for you. Okay, could you comment on the difference between those two?
Well, there is at least two major differences. One that is the most major is that while having the X-ray beam on and measuring, you cannot rotate the substrate while growing, because then you would lose the correct condition unless you were able to find a rotation that kind of keeps the stem in the correct condition. And that's bad because it could be that the beam fluxes are not completely isotropic on the way they hit the substrate. And I guess also that's maybe a minor nuisance, but the background, the base pressure of the MD at the synchrotron is lower because they cannot, or technically, even mount another buffer chamber and another load lock chamber at before the growth chamber. So I think too far higher pressure, which is maybe a nuisance. And yeah, and then they're gonna have the control over the what kind of impurities are introduced in their system, because they don't have any mass spectrometer to control what happens when the could have had like horrible substrate, but that, for instance, could have polluted the system.
Because now you say that you cannot rotate the sample.
No, yeah, you can, but you wouldn't do it because so you have to rotate, for instance, 60 RPM, for instance, to add very nice. So then it would be kind of hard to make sure that the rotation is not like wiggling, wide rolling or something like that. I think it's more a technical problem.
So the real question is, okay, if you told me that you measure the spectrum,
Yeah.
you could then measure.
Well, I mean,
Assuming the samples are
actually no, because yeah,
that is exactly what we gain.
yeah. Yeah, certainly.
Yes, yes.
And yeah, I mean,
Principally.
yeah.
Sorry. Yeah, no, it's fine. Showed a couple of papers on previous studies of dynamics of growth and CM. Before that, there's been a sequence of other X-ray experiments on static
Yeah.
stuff.
Mm-hmm. Yeah.
This time result. So there are other ways of doing interesting time result X-ray experiments, like common probe experiments. One thing to look at in wires. That's how to do X-ray.
I don't know.
Made any examples in literature?
I think I've never found any example with nanowires. Okay.
You have some of your predecessors.
Okay.
Someone market,
Okay.
make sure that resolution. Something, resolution.
Oh yeah, but it's not like as they grow. It's not like
No.
okay, yeah, no, I was
That's
thinking, oh yeah, okay, yeah. But you could use like I think a very fine and modern read reflection and energy diffraction setup could actually be used if it's not too noisy to monitor the dynamics of the nanowire inside NEMB as well. I think there are some papers out there where they actually do that for nanowires. Actually, no, for two-dimensional. But probably can also be done for nanowires if the noise is not too loud. That's, I guess, the main problem with the
That was an idea from the author.
yeah.
Maybe that's a good. Is there any interest in the audience in the room? Then I think thank you for your good answer. Photos are your PhD. So that's good. Let's see. I propose that we kick you out.
Okay.